And so welcome everyone, and thank you for joining this session. So today we'll walk through an end-to-end design workflow targeting GLP-1R, showcasing how generative AI can drive the de novo design all the way to synthesis planning. So we'll explore how Makya helps translate ideas into chemically realistic synthesis-ready molecules while keeping the design process intuitive and data-driven. So let's take a quick look at what we'll cover today. So we'll start by looking at the GLP-1R receptors, all the critical interactions in the binding sites, and what needs to maintain in order to design new analogs. Then we'll move into defining our generation strategy, how to decide what to optimize, and which constraint to set. After that, we'll explore chemistry-guided generation settings, detailing how we can control efficiency of exploration while maintaining diversity. And finally, we'll review the generated candidates and wrap up with how to prioritize synthesis-ready compounds connecting molecular design to real-world feasibility. So to kick off today's meeting, I just want to make a few comments about Iktos GenAI platform and in a high-level explanation on how it actually works. So everything starts with your target product profile. So you need to define it, and it can be anything from the crystal structure of your protein. It can be your ligand in 2D, 3D. It can be machine learning models. It can be your data set, chemical constraints, reactivity, among others. So once you set up this TTP, now we start with our generative AI with design novel chemical structures. But this generation isn't unconstrained because it's grounded in real-world chemistry. So basically, the AI will pull from a library of over 1 million commercially available building blocks and more than 2,000 organic reactions. So in other words, every molecule proposed is by design highly likely to be synthesizable. Then after we generate a batch of molecules, then we enter our optimization loop. So these generated molecules are scored using reinforcement learning based on how well they meet the target product profile criteria. So this scoring system acts like a reward function guiding the AI to prioritize more promising candidates in every iteration. So the result is a tightly integrated chemistry-aware design cycle that doesn't just generate ideas, it delivers optimized, synthesizable molecules that are aligned with real-world project goals. So if you want to have more information about our fully integrated platform, I invite you to scan this code or to click in the link that we'll share here in the comments. So here you will have more information about our latest webinars, benchmarks, and also explanations with the in silico experimentation. So let's focus on today's session, which is related with the GLP-1R. So this use case highlights the kind of problem solving that you can achieve in Makya when working with a challenging target such as the GLP-1R transmembrane protein. So GLP-1R is a particularly important target in the treatment of diseases such as type 2 diabetes. So let's take a closer look at how the peptide actually interacts with the receptor. So the GLP-1R receptor has two main domains, the extracellular domain and the transmembrane domain. The GLP-1 peptide engages both, which is crucial because the peptide effectively bridges both domains to stabilize the active conformation of the receptor. So there are several peptide-based GLP-1R agonists already on the market. However, there is a pressing need of developing new small molecules agonists. Currently, we have several molecules that are in the clinical development, and notably danuglipron, developed by Pfizer, showed a promising activity, but was unfortunately discontinued after phase 3. What's notable is that these molecules achieve peptide-like activation to engage key residues deep in the 7-transmembrane region. And the discontinuation opens a real opportunity because we already know the mechanism. The task now is to design new analogs that keep similar activation patterns but with improved design. So one of the key factors behind danuglipron's promising results is its strong overlap with the binding mode of the natural agonist GLP-1. So a crucial aspect of danolipron is its ability to form interactions deep within the receptor binding pockets through water-bridging contacts with residues buried in the transmembrane region. So this interaction helps stabilize the protein ligand complex, effectively mimicking the key contacts made by the natural agonist GLP-1. So additionally, the oxetane groups plays a key role, enhancing potency by enabling additional hydrogen bonds. So with this molecular understanding, we can now design molecules that reinforce these key interactions from the very beginning. So with this in mind, if we want to design new compounds using danolipron as a reference ligand, it is crucial to retain both the carboxylic acid and the oxetane as starting points. So we applied a fragment-based approach to generate molecules using these key functional groups as the core elements. So let's move now into the design phase and see how we can translate these structural insights into an AI-driven generation strategy. So our objective is to target specific residues that are known to interact with a reference ligand, such as tryptophan and serine, among others. So these form a stable interaction network anchoring the molecule within the binding pockets. But we don't only want to replicate what it exists, we also want to discover what new interactions we can reach within the binding sites, such as the residue losing 217, allowing us to generate a more diverse set of molecules. So in Makya, we'll then combine three components to drive this design. First, a fragment growing generator starting from our defined core. Second, a QSAR model that guides optimization towards activity. And third, a structure-based rewards derived from docking and key protein-ligand interaction fingerprints, ensuring that the generated molecules maintain favorable interactions, including the new ones such as losing 217. So now we will switch into the software. So here what I'm going to show you is all the modules that you can explore with Makya and all the possibilities that you have to work with our platform. So in Makya, you have different kind of modules in where you can work. And so let's start with the first one, with the project data. So by uploading data, you define the chemical space where your generation will take place, and you can use it later as well to train your own predictive models. You can also integrate your own pains and talks dictionary, ensuring that the generated molecules stay within a safe, relevant boundaries. Then you can add docking files to enable 3D guided generation, and also use QSAR models to train optimized machine learning models that can guide molecular scoring. Then you can also play around with your retrosynthesis preferences, for example, to account for building block bioavailability, reaction type, provider, maximum number of depth, etc. Makya offer both the 3D ligand-based and the 3D structure-based modules to guide the generation through 3D shape similarity, pharmacophore, docking interactions, and protein-ligand interaction fingerprints. You can even score molecules independently using any combination of RD kits, QSARs, 3D, or APIs-based metrics. And finally, you're ready to launch your generation and explore a new wave of design possibility with Makya. So now that we already explore what you can get with Makya, let's go back into our project, which is the GLP-1R project, and look at how we apply all this workflow to design better molecules. So in Makya, structural information can be directly used as reward functions to guide molecular generation. So here you have two rewards that we use to optimize molecules. On the left, through MDAT docking, where each generated molecule is automatically docked during the run. And on the right, through fingerprint-based interaction analysis, which quantifies how well new compounds reproduce critical ligand protein contacts. So this approach allowed us to bias the AI towards molecules with the key interactions that you as a user want to retain. So once again, let's switch into the software so we get to see how this actually works. So if you want to work with the 3D structure base, the first thing that you need to do is, of course, upload it into a software. So to do so, you need to have your PDV and SDF of your protein. Once you do that, you can upload it into our platform, and then Makya will show you, and you'll be able to visualize the reference ligand inside the protein pockets. And for example, here, as you can see, we're also going to work with water molecules. Then you can explore different kind of interactions with different residues in the protein pockets and play around a bit with the visualization. So one consideration before we move forward into the following settings, in Makya we have two softwares that you can use. It's either Bina or RDoc. So by setting up these constraints, you are setting up the first reward, which is the docking software. So the next step is you need to tell the software now which kind of interaction fingerprints you want to work with. So in order to do that, we need to go into the 3D structure-based module. So here we're going to create together a new project. For that, I'm going to add the day of today, webinar demo, and then I'm going to choose the software tool, the docking tool that I'm going to be working with, which is RDoc in this case. Then after that, I'm going to select the protein and ligand that I already created. And by clicking on next, now you will see that Makya will redirect me into the visualization page. So here, what we will see, it is very cool actually. You will be able to visualize your reference ligand inside the protein pockets, and also you will get to see all those residues with non-covalent interactions with your ligand. So the way that we work in Makya is to prioritize those interactions that are important for you. So the way that it works is we give a systems of weights. So the higher the weights, the most important the interaction is. So for example, here we have the region of the oxetane and the carboxylic acid from which we're going to start growing our fragments. So we're going to focus mostly in this area of the protein pockets, giving certain ways and certain interactions to drive the optimization of the molecules into that pockets. So to do so, here you will see me giving different kind of ways and deactivating certain interactions that are not important, or they are not in the place of the protein pocket that I want to target. So to do so, I am gonna increase the weight and deactivate those that are not important. So as you can see here now, the visualization of the residues that I gave a weight of 3 increases inside. So then I'm going to do the same with the pi stacking. Here I'm going to give an interaction 4 of this residue. Then another important thing that you can achieve with Makya is that if there are certain residues that they are not present in the interaction fingerprint that we are showing you here, you can actually add them. So I'm going to do exactly that here. So I'm going to choose the kind of interaction, which is the pi stacking, the residue, which is the residue 33, and the atoms that I want to use for the interactions. And in this case, I'm going to give a high weight because this interaction is actually very important for me and for the generation of molecules. Then we're going to continue with more or less the same logic, and we're going to deactivate or give high weights to all those interactions that are important. So here, once again, I'm going to give I'm going to find for the key residue, the lysine 217, the one that I mentioned before, and I'm going to add it one by one, the atoms that I want just to target during this interaction. So as you can see here, you have to add it 3 times, and once you're done, you will increase once again the weight of the interactions. And in this case, we are done. We already have the interaction fingerprints that we want to target during the generation. So after that, the only thing that you need to do is to save, and you are ready to proceed with the generation. So going back into the presentation, now that we have the 3D structural base, also I mentioned that we're going to be working with QSAR models. So in Makya, you can create your own QSAR models as well if you have your data sets. These QSAR models, they can be, for example, to predict biological activity or even admin properties. So once again, I'm going to show you in the software how you can achieve and you can build these models. So the first thing, of course, that you need to do is to start to add a data set, because in order to create your QSAR models, you need a minimal of data points just to start with. So here in Makya, For example, I already uploaded a CSV with different kind of information, and here you can visualize all the molecules, and also you can see the different kind of targets. For today's presentation, I will be focused in the PEC50 just to predict the activity. So once you have your data set in Makya, now you need to move into the QSAR. And here we will create again a project together, which I will call again webinar demo. So once you do this, now you can select the target that you want to work with. Like for in this case, the data set, I'm sorry, in this case is the one that I just showed you. And then you will select the target, which is the PEC50. So in Makya, we work with continuous classification models. So it means that you need to give the software a threshold from where you are going to distinguish between active and non-active molecules. For example, in this specific case, I'm going to give a threshold of 8.5. So I will have 41 active molecules and 23 non-active molecules. So just with that information, it's enough to start to train your model. And the only thing that you need to do is to click run. So for this specific case, I already trained a model. And so with this, once it's trained, we are going to give you the information, like different kind of metrics, like for example, EUC, precision, recall, F1 score, different kind of plots, like for example, precision versus recall, confusion matrix, because you as a user will evaluate if the QSAR model is good enough to be used as it is, or if on the other hand, you need to train it again with a different threshold, for example, or including or removing data sets. So once you do this, once again, you are ready to start with the generation. But before that, we need to tackle one more point, and is like the starting point. So since we are doing initial fragment, we need an initial starting point from where Makya can grow your molecules. So we have two different strategies here. The first one is an expansion starting from a piperazine, and the second one is a ring closure. So to decide your initial fragment, you can use many tools, like for example, your chemical intuition, but in some cases, maybe it's a bit tricky just to know exactly what initial fragment to use, like for example, for this ring closure. So for that, we also offer another software, which is Paya, which complements Makya by assessing the synthetic feasibility of molecules. So basically, it evaluates potential synthetic routes and helps identifying suitable starting materials that are going to be used, for example, as starting points. So once again, I'm going to present you our software, which is Paya. And the only thing that you need to do here is to enter the smiles of your molecule, or you can draw your molecule as well, and then you press start, and you will start with the analysis of the retrosynthesis. So what Spaya will do here is it will find all the ways that it can imagine just to generate or to give you different kind of retrosynthesis analysis. It will arrange them into cluster with respect to the R-score. So the R-score is a proprietary tool from Iktos that basically is going to tell you how synthesizable that molecule is using that specific route. Like for example, an R-score of 0, it means that the algorithm is sure that the molecule is not synthesizable, and an R-score equal to 1, it means that the algorithm found an exact match. So for example, if we take a look here, and we click in this cluster, we're gonna see a synthesis with only one step. If you click in reference, you will be able to see all the kind of references for this disconnection with the name reaction, the patent, and also, if possible, also the process and the way extracted from the patent. So then, if you click in your initial materials, you will have the information about the providers that we have in our data set, also the price per gram and the delivery time. And in this case, this compound is a literature compound, so it means that we can continue searching more routes from here and ask Spaya to give us more different kind of disconnections. So for example, here, this is exactly what we are gonna do. And so Spaya here found exactly what we were looking for, which is a way just to use an initial fragment to proceed with a cyclization. So as you can see, Spaya, it is a good tool not only to find retrosynthesis route, but also to find initial fragments in the case that it's not so intuitive. So with this being said, I'm going to move back into Makya because now what we're going to do is we're going to build a generation together, starting from the very beginning. So again, here I'm going to create a project, webinar demo. And then in Makya, we have three kind of algorithm, which is the fragment growing, the fragment linking, and the fine tuning. Since we are doing fragment growing, of course, we're gonna work with this algorithm. So after that, we're gonna be redirected into the generation settings. Here we have a lot of settings. We won't be able to go through all of them in this webinar, but we will explore them in the upcoming ones. So let's start with the reactive center or the chemical constraints. So of course, the first thing that you need to do is to insert your initial fragment from where Makya will grow your molecules. In this case, it's the one that we found in Spaya. So if then we go back to Spaya, we also have 1 and 2 steps. So in this case, we're gonna ask to have at least 2 generation steps to make sure that we are achieving these kind of molecules. And like this, you would be able just already to start with your generator. However, we also want to give the chemist the possibility of telling the software from where exactly which atoms are participating in this reactivity. So you can do so by telling exactly the atoms that they're going to participate in the reactivity. Like in this case, it's the nitrogen, the 2 carbons and the nitrogen here. So in this way, Makya will know that only this atom will participate in the reactivity, in this specific case, the ring closure. So with this information, you're already setting up the initial fragment, and now you can also apply constraints to the point of view of the building blocks that you're going to work with. So we have physical chemical descriptors, and also we have substructural constraints, like for example, the substructures that you want to see or you don't want to see. So in this case, for example, I'm going to work with a maximum of 3 number of rings in my building blocks. Then you can translate exactly the same into your product constraints. So for example, here I'm going to work with a maximum of 8 number of ring, 11 number of rotatable bonds, a minimum of 0.3 of QED, and 650 as a maximum molecular weight. Then after that, the same as with the building block, substructures that are absolutely needed or forbidden. And then paints and talks. As I said before, the paints and talks is a list of substructures that you don't want to see in your generated molecule. So the way that it works in Makya, you will input this list, Makya will generate molecules, and then will clean up all the molecules that are matching this list. So now that we have all our chemical constraints, we need to move into the rewards. So in the rewards, the first one that we have in our list is the QSAR. So in this case, you only need to add the QSAR that you already trained, and then with the 3D structure base, the same. You need to add the one that we've created together here, and you can visualize all the contact score that we added in the previous step. To generate molecules, you need an anchor. So Makya is able to compute the reward function. So in this case, I'm going to use the anchor from my initial fragments. And like that, you're ready to go and you're ready to start running your generator in order to generate molecules based on building blocks, organic reactions, and then optimization of the reward functions, which are QSAR and 3D structure base. So to do so, the only thing that you need to do is to press run, and the generator will automatically start. For the purpose of today's webinar, I already run different kind of generators, so I can show you exactly how it looks. So the molecules in Makya, they're going to be listed based on different kind of metrics, like for example, Iktos ranking, which basically will tell you how optimized your molecule will be against your rewards. It can be also against docking score, machine learning models, confidence, and so on and so forth. So this is a way for you in order just to filter and take a look of your molecules around. Then you have also, for example, the parallel coordinates, and with the parallel coordinates also you can filter your results based on different kind of threshold. So in this way you can explore the results that you only want to see for yourself. So I'm going to show you the molecules that I personally selected from different kind of generators. And for example, here, this first molecule, if you press C detail, you will have the information of how the algorithm generated and then how the algorithm docked it inside of the protein pockets. And very importantly, this molecule, as you can see here, is giving us the interaction that I was looking for. Then the other thing that you can do with the molecule is to send it to SPIA. And so if you click in this button, you will be redirected into SPIA, and SPIA will give you different ways of synthesizing or retrosynthesizing your molecules. Like for example, here with the ring closure that we wanted to target, starting with different building blocks and different reaction steps. Okay, so now that we went through all of these generation and all the steps that you can follow in order just to get your molecule, I'm gonna show you now the molecules and analyze the results in order just to find the promising candidates and the way that we work internally here at Iktos with our platform. So here you will see the selected molecules generated by Makya compared to the reference ligand. So in this first slide, and here I'm presenting you 4 molecules. So important just for you to know that this was a first iteration. So here we are not looking for any decoration. We just wanted to have ideas of different scaffold and that Makya generated. So it's a selection that I did starting from the piperazine, and then I did the same starting from the ring closure. So here we had the consideration of, for example, the impact of the orientation of the substituent, interaction made by the ring, and the synthetic accessibility as well. So for all these selected molecules, of course, as you can see here, we took 2 main directions. So for example, in the first one, we have geminal linkers, where substitution increases, for example, local rigidity or might improve receptor alignment. And in the second focus, is the linker flexibility, because you can explore variants that could better accommodate the conformational changes. So these follow-up compounds are excellent starting points and served as an inspiration for a manual curated list of targets for further exploration. And that's what we did. We created a curated series derived from Makya suggestions, like of the geminal substituents aliphatic ring. So each analog, we fine-tune the linker length and hybridization to adjust orientation. So these steps actually illustrate how AI-driven design complements chemist's intuition, and it's just acting like a design tool in order to make more efficient the way that you work. So here Makya proposes patterns and we expand upon them with the human insight. So finally, in this video, what I wanted to show you is a sequence where you see the reference ligand, and then you will see the 2 analogs that I chose. And the first one here is a perfect example of Makya's abilities to explore new chemical ideas without losing essential contacts and enforcing the generation to explore new ones, such as tryptophan or lysine 217, which are not present in the reference ligand. The second molecule that you want to see in just a second shifts slightly deeper in the cavity thanks to the 2 atoms in the linker, reaching further into the protein pockets, but once again, showing these novel interactions that we were looking for. So the message here is that altogether, these 2 poses, they overlay remarkably well with the reference ligand danulipron, showing how Makya's AI-driven generation not only diversifies the structure, but it also preserves the 3D structure-based relevance and the 3D structure base that you want to see. So just the final few minutes of the webinar. We explore how we can start like the main problem, how we can use our workflow in order to solve it. But now the question it would be, okay, how can we explore if the molecules that we've selected, they are actually synthesizable? So first thing in Makya, we are going to give you always the retrosynthesis goal. But in order just to prioritize synthesis, you can also use SPIA, which I already presented to you. So SPIA, with using SPIA, you can evaluate different kind of retrosynthesis using your chemistry intuition, your chemist insight. For example, you can look for routes with maximum number of steps, with maximum price per gram, for example, with different providers, packaging. Also, if you have certain name reactions that you want to proceed with or you want to forbid because you don't do it, you can also look routes like that. Also work with intermediates, like in our case that we have these intermediates with just to proceed with the ring closure. And after that, SPIA will give you the results as I show you, with different kind of routes that you can explore and take the best out of it. So for example, you can prioritize the synthesis, depend on the route depth. For example, in these initial stages, we would target, of course, the for short and simple synthesis because we are doing exploration. You can also target in the prioritization with the price and availability of starting material. For example, this it's a bit more expensive than this one and the delivery time as well. And finally, SPIA will also give you the reference and the name reactions of all the disconnections so you can prioritize on the required chemistry. So as a conclusion of all of these, what the message that we want to give you is that Iktos AI platform, by using it, what we want to do is to support the chemistry, of course, and just to act like a tool for you for the design and just to improve the way that you work in your everyday life. So that would be it. And now I'm gonna give back the word to Elle so we can proceed with the Q&A. And thank you very much for your attention.